Hi folks, we're going to take a look at page 194, number 13. So they're giving us that a cylindrical tank with height 15 meters and diameter 2 meters is being filled with gasoline at a rate of 500 liters per minute. Okay, so before I start even thinking about a solution here, I'm going to start with a diagram. So I've got a cylindrical tank, okay, and we know that the height is 15 meters and the diameter is 2 meters. Okay, now right away I'm going to put in that my radius is 1 meter, okay, since I'll likely be working with the radius instead of the diameter. And we're being told that it's being filled at a rate of 500 liters per minute. Okay, so that mathematically represents the derivative of the volume with respect to time. Okay, so it's how the volume is changing with respect to time, which of course you can see by looking at the units. So here, that is 500 liters per minute. Okay, now before I go on, and they give us a hint in this question here by telling us that 1 liter is 1,000 centimeters cubed, but here my height and radius are given in terms of meters, so I'm going to want my volume to be in terms of either centimeters squared, in which case I'll have to change these into centimeters, or meters squared, and I can leave these as they are. So I'm going to try to go for meters squared here. So first, let's start with the conversion they give us. So each liter is 1,000 centimeters cubed, so this is going to be 500,000 centimeters cubed per minute. Okay, and I want to turn this into meters cubed. Okay, so in other words, the number that I should end up with here should be smaller, actually much smaller than 500,000. So that gives us an indication as to how we're going to do the conversion. So we want to turn this into meters cubed. Okay, so we're going to replace centimeters cubed with meters cubed. So in the denominator, we have to have how many centimeters cubed in a meter cube. Okay, and if you think about a little cube, okay, say this is 1 meter cubed, that means each side length is 100 centimeters. So 100 times 100 times 100, okay, which is going to be, well, 10 to the 6, so 1 with 6 zeros. So I'm going to be dividing this by 10 to the 6 centimeters cubed, okay? And so here we've got 500,000 divided by a million, so don't need my calculator for that. That's just going to give me 0.5 meters cubed per minute. Okay. Now, depending on what science classes you're taking, you might be able to do this conversion, very quickly in your head. But I just want to show you an intuitive way to figure out how to do that conversion. Okay. So now we've got everything in the same units. We can go ahead and try to solve the problem. Okay. So they want to know at what rate is the fluid level in the tank rising. Okay. So in other words, if you've got fluid in the tank, okay, they want to know how the level is changing. In other words, they want to know how this height is changing with respect to time. Now notice here that regardless of how much liquid is in the cylinder, the radius always stays the same. Okay, so this makes it a little easier than, say, the cone question where the radius was also changing with respect to time. But here, because it's always a cylinder, always has the same radius. Okay, so now we have to relate the two rates that we're given and looking for. So we're given volume and we want to find height. So the relationship between volume and height, of course, is given by the volume formula of the cylinder. But again, we can simplify this because now I'm looking at the volume of the water here, or the gasoline, I suppose. And we can simplify it because we know that the radius is 1. Okay, so the volume can be simplified to pi h. Now, notice here, they didn't give us any other information. Normally they say when the height is or when the radius is. They don't do that, but I shouldn't be too surprised because if you look at this relationship, it's a linear relationship. Okay, so we should be able to solve it without needing any other information. Okay, so now they're giving me dv dt. I'm looking for dh dt, so we're going to take the derivative with respect to time of both sides. So I have dv dt on the left-hand side. On the right-hand side, of course, I have an expression in h, so please be sure that you're using the chain rule. So first I take the derivative of pi h with respect to h, which is just pi, and then I take the derivative of h with respect to t. Okay, so it's a very simple relationship between those two rates. And of course, they give me the derivative of volume with respect to time, which is 0.5. Okay, and so the derivative of height with respect to time is 0.5 divided by pi, but that can be written a little nicer. We'll write it as 1 over 2 pi. So dh dt, okay, the rate at which the water level is rising is given by 1 over 2 pi. And now we'll put in the units so we know that it's height. So we're talking about meters per time unit, which in this case here was minutes. All right. Now there is another question they ask us. They say about how long will it take to fill the tank? Okay, so we have the rate at which the volume is increasing, and we can find the volume of the tank itself, and then with that we should be able to calculate how long it takes. So let's start by calculating the volume of the tank. Okay, because we want to fill it up, so we need the volume of the full tank. So again, pi r squared h, and here r is just equal to 1. So that doesn't contribute, and then the h is equal to 15, so 15 pi. All right. So now I know the rate of change is 0.5 meters cubed per minute. Okay. So how will we get that? Since I think we can assume, but they haven't told us that the rate at which the volume is changing itself changes. It's constant at 500 liters per minute. Okay. So we take the total volume. Okay. And we divide by the time. So in other words, if I solve this here, the time it takes will be 15 pi, okay, divided by 0.5, okay, and that's approximately equal to, okay, again, we can use approximations because we're working with an application question. So here we've got 15 times pi divided by 0.5. Okay, so it looks like we got about 94.25 minutes. Okay, and in fact, on this side here, an approximation would have been perfectly acceptable. So here, in fact, let's do that. 1 divided by, open bracket, 2 times pi, and we've got it's about 0.16. So if we go back here, that's approximately equal to 0.16 meters per minute. Okay. So again, just a recap of what we did. We set ourselves up with a diagram. By doing that, it was very easy to see that the radius of the gasoline would just be the same as the radius of the whole tank. Okay. We found a relationship between our two values, and then from there created a relationship between their rates. Okay, so that's it for now.